Okay, so in this video, what we're going to be doing is actually continuing from the last video. In the last video, we left off solving the first part of this problem. The problem reads, if v is the free velocity of a particle and beta is equal to 1 minus v squared over c squared raised to the power of minus a half, prove that v dot dv dt is equal to v times v dot and v dot d of beta v dt is equal to beta cubed times v dot. Now, in the last video, actually, I forgot to mention that this is a three-part problem. So there's a third part that I didn't write down. So I put that up now, and it reads, also show that v dot f is equal to m dot c squared. Okay, so in the last video, the way we solved the first part of this problem, what we did was actually we considered, rather than taking the dot product between the free velocity and its time derivative, as it asks us to do over here, what we did was actually take the dot product between the forward velocity and its time derivative. Okay, so the forward velocity, capital V, let's use white, capital V, we dotted it with its time derivative. Now remember, when you're taking the time derivative of four vectors, you take it with respect to tau, right? Tau is the proper time. Yeah. So the time derivative of the forward velocity would be dv d tau, not dv dt. Okay, so dv d tau. Now, we saw that the time derivative of v, the forward velocity, we actually have to apply the chain rule. Okay, so the chain rule provides that dv d tau is equal to dv dt dt d tau, where dt d tau is equal to beta. Okay, so that implies that v dot dv d tau is equal to, I'll put that down here, is equal to v dot beta dv dt. Okay, the v's here are still the four velocities. So what we're going to be doing is actually using this same method in order to prove this relationship here. Okay, now if you recall, the forward velocity v, let me write that in a different color here, v is equal to beta, and then what we have here is the components of the forward velocity, v comma ic. Right, so we have a beta term multiplying by v comma ic. Now, v here is the free velocity. Okay, and it has components v sub x, comma v sub y, comma v sub z. Okay, so all of this is in this v. I simply didn't write it out in order to save on too much writing. So the forward velocity is equal to beta multiplied by the free velocity as its first component, and then beta multiplied by ic as the fourth component. Okay, the first through third components are down here, and they're composed inside of the free velocity. So what we're going to do is we're going to substitute this forward velocity term into this equation. Okay, we're going to substitute all of this into here and into here. Okay, so this gives us, let's use white, this gives us beta times the components of the forward velocity, v, ic, dotted with beta times dv dt. So I'll just write that as simply as d dt of v comma ic. Okay. So we can write this as, in fact, we can write this whole term as beta times dv dt comma ic. Let's see here. Oh, whoops, I forgot the beta term over here, so I have to include this. Let me just go back. So what we'll have is beta times d of beta v dt comma beta times ic d of beta dt. Okay, so all of this is being dotted with beta v comma ic beta. Okay, if we carry out the dot product, we end up with beta squared as our first term times v dotted with d of beta v dt, and then ic multiplied by ic gives us I squared c squared, and I squared is negative 1. So what we get is a negative beta squared c squared times d beta dt. Okay, this is all equal to v dotted with dv d tau. Okay. Now, if you recall from the last video, we had an identity for this term here. And that identity was that dv d tau dotted with v is equal to 0. Right? The dot product between the floor velocity and its time derivative is equal to 0. Now, if this term equals 0, then we can go ahead and cancel out the beta terms so that we're left with v dot d beta v dt minus c squared d beta dt is equal to 0, which implies that v dot d of beta v dt is equal to 0. I'm sorry, is equal to c squared d beta dt. Okay. Now, in the last video, we actually also came up with another identity, and that identity was for this term right here. Okay. So the identity was that d beta dt is equal to vv dot divided by c squared all over 1 minus v squared over c squared to the power of 3/2. Okay. Now, we can write this as v dot times v over c squared multiplied by beta cubed. Okay, where beta cubed is the 1 over 1 minus v squared c squared term. Okay, remember, beta is equal to this term here, and so if we cube that term, we get 1 minus v squared over c squared to the power of minus 3/2, which is what's over here. 1 over 1 minus v squared over c squared to the power of 3/2. So we can replace this with vv dot over c squared times beta cubed. So if we do that, we'll have v dotted with d of beta v dt is equal to c squared multiplied by vv dot over c squared times beta cubed. Okay, and our c squares cancel out. So this just leaves us with the term that we're looking for, right? v dot d of beta v dt is equal to v times v dot multiplied by beta cubed. Okay? So we've managed to prove the relationship. Now, as I mentioned, we're going to consider the third problem in the next video. We're not going to do it over here. Some of the mathematics got actually quite messy, but usually in special relativity mechanics, the math tends to build up. So I hope you were able to follow along.